Bitteschön. Good afternoon, grade 10s, and welcome to another physical sciences lesson. Today we're going to look at electromagnetic waves. So on Monday we looked at transverse waves. Yesterday we looked at longitudinal waves. And so today we're going to look at electromagnetic waves. I hope you're ready for some thinking because there's quite a lot involved, okay? So before we start, please make sure that you've got your Q&A section open, all right? You will notice that our amazing moderator has already given us the africanteamgeeks.co.za link, all right? And I have posted already for you in the Q&A the team's link for tomorrow, as well as the link for the drive where all the resources are stored. Okay, that link is the same as it was on Monday as well as on Tuesday. So if you have that drive link already, you don't have to download it again, but please take note of the link for tomorrow's class. Okay, I will post them again at the end, I promise. All right, guys. Remember to use the Q&A, say hi, you know, let me know that you're there. If I say anything that doesn't make sense and you need some extra help, let me know that too, so that we can have some fun today. Okay, right. So let's start with electromagnetic waves. Okay. Now you'll notice that this word has two parts in it, electro and magnetic. And that is because the electromagnetic waves consists of electric fields as well as magnetic fields. And so we decided, I say we, scientists decided to name them electromagnetic waves. For those of you following in your textbooks, this is in the Oxford Successful on page 98, and in the Study in Master, I'm assuming it's round about page 120. Again, guys, remember, I only have an electronic version of the Study in Master, which doesn't have the page numbers at the bottom. So I use the teacher's guide and work backwards from there. Okay. So, important to note is that electromagnetic waves can travel through a vacuum. This is not true for longitudinal waves, and this is not true for all transverse waves. Someone wants to know what page? I'll repeat it, but it's on the screen. Hi, Ashley. Hi, Arthur. Good to see you guys again. Hi, Hugh. There we go. You see, guys, I'm starting to remember to put the pages in. Okay, cool. So that is important to note about electromagnetic waves. They can travel through a vacuum. That means that we can't always predict them. We can't see them. Okay? And so we have had to, again, I say royal we. It's not royal we. It's the scientists that came before me. They have scientific models that they designed to help us understand the behavior of electromagnetic waves. Okay. Come on, PowerPoint. All right. So the first one of these two models is the wave model. Okay. So we say that electromagnetic radiation, EM is for electromagnetic, radiation is just a fancy word for waves. We say that electromagnetic radiation can bend like a wave, okay? And the example we use is when light enters your eye, The lens of your eye bends the light and forms an image at the back of your retina. Okay, this is how we see. But we also have particle models. Okay, so let's just quickly have a look. We have wave models, which we use to say that electromagnetic waves act like waves, right? But interestingly, electromagnetic waves also act like particles, okay? They can transfer energy. You've ever wondered about that? You stand out in the sun and you have the sunlight on your skin feels that warmth, and that is the transfer of energy, okay? We're going to use another example of the eye. Those in the energy that light transmits or transfers activates the cells in the back of your eye on the retina that help you to see. Okay, so not only is it important that electromagnetic waves can be bent so that you can see a nice picture on your retina, but it is also important that the electromagnetic waves transfer energy to activate the cells that form the picture. Okay, so now I've given you two models that we use to explain electromagnetic waves. Okay, so what we do from there is we say that electromagnetic waves has wave-particle duality. Now that's quite a big statement. Let's just think about it for a second. We gave the wave model and we said electromagnetic waves behaves like waves because we can bend them. We then said electromagnetic waves also act like particles because they transfer energy. Okay. The word duality, dual, is between two. Okay. So wave-particle duality means we can explain and describe electromagnetic waves using both of these models. Miss P, Ollie, Aaron, Vincent, Jared, we are looking at EM waves. I can go back a slide for you. Is that far enough, sweetheart? Good. So again, guys, we're doing electromagnetic waves. We looked at transverse waves on Monday and longitudinal waves on Tuesday. And now we're looking at electromagnetic waves. Ruben, this is page 98-ish in Oxford. Okay. Is everybody caught up? Okay. So let's now give the definitions of this duality. Okay. So some aspects of EM waves are better described using the wave model. Other aspects are better described using the particle model, and therefore we say it has dual nature. Dual, two. Okay, it has the nature of both waves and particles. And this is a super important concept. Okay, because this informs what electromagnetic waves do. Okay. Now, don't panic, don't panic. I'm going to show you in a few slides what an electromagnetic wave looks like if we could see fields, okay? And I'm going to explain it to you slowly, and then I'm going to use that explanation to explain to you how electromagnetic waves travel through a vacuum, okay? It's a question they like asking, all right? And electromagnetic waves is important for grade 12, okay? So just follow with me. When an electric charge accelerates, it causes a magnetic field. Oh, sorry, sweetie, the delay. Okay, hang on. I know. Yeah. When are we going to do magnetism? Next week? Is that the right slide? Sure, this delay is terrible, guys. Guys, I think if you need me to go back to a slide, okay, what you do is you tell me what that top heading is, okay? So you tell me what the top heading is and say, ma'am, please go back to the wave model slide, okay? Then I have a bit more of a chance to get the right slide, okay? You got it, sweetheart? I hope so. Oh, this is hard. You guys are doing so well. I can only imagine how hard this delay is. It's tough for me too. Okay, we good? Right. Okay. So, wave duality. Now I know this is tough, guys, because the problem is you can't see it. But we're going to try. We're going to try. When an electric charge accelerates, it causes a magnetic field. This is a concept that you're going to learn about in grade 11. It is tough, okay? I'm not even going to lie to you, okay? But it is so important when you go to grade 12s when you do motors. So this electric charge creates a magnetic field. And the magnetic field causes an electric field, okay? This has got so much to do, like to explain this to you guys is like really, really tough, okay? And I apologize that I don't have a better answer for you from this, okay? So you have an electric charge, it accelerates, which causes a magnetic field. The magnetic field then causes an electric field, okay? So now, the charge accelerates, and instead of just causing a stationary field, it accelerates to such a point that it disrupts the fields and causes them to oscillate, causes them to vibrate, causes them to have a wave pattern, okay? And that is the crux of electromagnetic waves. It is not only the magnetic field and the electric field. It's the fact that this charge accelerates and disrupts these fields to cause them to vibrate, to oscillate, to make a wave. If you think about it, it's a little bit like you running through the water, okay? If you walk slowly through the water at the beach, then the shape of the water doesn't change much. But when you run through it, then you change the shape of the water where you were quite significantly, okay? And that is what this little charge here does. So, I told you, don't panic. This is the model we use to describe electric fields, okay? So I'm going to go through it slowly, and then I'm going to type it out for you. Okay, well, it's already typed out, it's on the slide. All right, so don't worry about the wavelength. Okay, you really don't have to worry about the wavelength here. So the red thing, the red one is the magnetic field. And the blue one is the electric field. And the charge, the electric charge, is accelerating from the bottom left of your screen to the top right of your screen. Study and Master 126, if I remember correctly from someone. Okay, so this particle accelerates from the bottom left to the top right, okay? As it accelerates, it causes this magnetic field. Got it? This magnetic field here causes that bottom electric field. Okay? And because there's now an electric field on top of a magnetic field, the magnetic field flips to the other side. And it has its little half a pulse. This magnetic field causes that electric field. That electric field causes this magnetic field. This magnetic field causes that electric field, which causes this magnetic field, which causes that electric field. Okay, so each little half of a wave causes the next part of the opposite one. Can you see that the magnetic field is 90 degrees to the direction of propagation? The electric field is 90 degrees to the direction of propagation. And if you look here and here, the electric field and the magnetic field are 90 degrees to each other. Okay, so I'm now going to give you guys this in word form, all right? So we call this propagation of En fields, okay? So that diagram shows the wave traveling in a straight line. Remember, bottom left to top right, okay? At right angles to the direction of propagation is an oscillating electric field. It oscillates with a transverse wave motion. I'm going to go back to the diagram and just show you what I mean by that. If this was a longitudinal wave, you would have seen squash and release and squash and release, okay? But you're not. You're seeing displacement away, back towards, displacement away, back towards, okay? So that is why I am saying, I get you, Ms. P. That is why I'm saying that this is a transverse waves, okay? And not a longitudinal wave, okay? So, Ms. P, I know how hard this is, okay? I understand so much of how hard this is, okay? And the problem is that you guys haven't done electromagnetic induction, and if you've done electromagnetic induction, then it's easy, okay? And I'm so sorry that they've put the curriculum together like this. I know my kids also struggle with this. So let's just talk through it again. This line here represents an electron that is accelerating, let's say from the sun down to the earth, okay? Because it's an electron, it causes a magnetic field. Because it is accelerating really fast, it causes the magnetic field to form a wave pattern, an oscillation. Okay. But magnetic fields cause electric fields, and electric fields cause magnetic fields. Okay. This has got to do with electromagnetic induction, okay? This is what is used when we change mechanical energy to electrical energy by using a generator, okay? The generator causes the magnetic field, which then causes the electricity to flow. I hope that makes a little bit more sense. I know this was hard, okay? There is a word for it, okay? I'm getting to that word now, Ms. P, I promise. And if you get that word, I promise you'll understand this. Okay, so we said at right angles to the direction of propagation, I have an oscillating electric field. It oscillates with a transverse wave. At right angles to the direction of propagation is an electric field. It also causes an, oh, I double typed here. No, I didn't. At right angles to the direction of propagation and the electric field, we have a magnetic field. The magnetic field also oscillates with a transverse wave motion. So we've got three different things here. We've got the direction of propagation. 90 degrees to that, we've got an electric field. And 90 degrees to the direction of motion and the electric field, we have a magnetic field. Okay. So we say that the electric field induces, it's a big word, it means causes, okay? The electric field is the reason why there is a magnetic field, okay? That's why we use the word induce. And we talk about electromagnetic induction in grade 11 and 12, okay? So the oscillating electric field induces a magnetic field. Equally, the magnetic field then induces the electric field, okay? And so what we say is they are mutually regenerating. The two oscillating fields keep on producing each other, and therefore they are called mutually regenerating. Ms. P, I hope this slide helps a little bit more to explain the diagram. All right, guys? Everybody okay? Okay. Now, this last sentence here is mal belangrik. Okay, it is super, super important. There's electroinduction. Ollie, it's electromagnetic induction. Okay. So this last sentence here is important. EM waves do not need a medium. And the reason they don't need a medium is because they have these two mutually generating fields. Okay. Ollie, electromagnetic induction is grade 11 work. Yeah, Miss P, I know it's tough. It's tough. Okay, right. Now, this is fact, it is rule, it is not debated, okay? The speed of light. You should have heard of the speed of light, okay? So all electromagnetic fields travel at 3,0 times 10 to the power 8 meters per second, okay? That is 300 million meters per second. That's woestvinnig. That's very fast, guys. Okay. Now, don't sit there and go, oh, nog iets wat ek moet onthou. Another thing I have to remember. This is on the information page. And it is called the speed of light in a vacuum. Does medium affect it though? No. I know, guys, this is really, really hard, okay? I know this is really hard, okay? So, the symbol we use for the speed of light is little c, and it's on the information page, okay? So you don't have to remember that value. It will be given to you. Okay. Erin, that's a nice way of putting it. Erin says once the electron gets moving, the two waves keep supporting each other. That's exactly right. They keep on supporting each other and giving each other energy to carry on. And when the one's got energy and the other one runs out, then this one helps that one out. Okay, so yes, it is two waves supporting each other to keep on going. Good job. Good job, Erin. Okay, so electromagnetic waves, the speed is given. Right. Now, something that you might not like. Lots of information. Okay. When we talk about the electromagnetic spectrum, we talk about all the frequencies of waves in the electromagnetic spectrum. And there's a lot. Okay. There's a lot of frequencies. And unfortunately, you need to know some of this. Okay. Now, don't try and memorize all of it because that's going to blow your brain. My suggestion is that you first memorize the names in order. Okay. Explain the speed of light. Sure, that's a hard one. That's experimental. They did lots and lots and lots and lots of experiments, and they figured out that EM waves moves at a certain speed. So Tumelo, no, the speed of light, we don't really have. The speed of light doesn't really change. Oh, guys, I'm sorry. You've got textbooks that don't quite explain it. I'm sorry. Okay. All right. So, electromagnetic spectrum. Don't try and memorize all of it at the same time, okay? Try and memorize the sequence of the names, and then try and add either the frequencies or the wavelengths. And you can calculate the other one, okay? Right. So, don't panic. Don't panic. This is the entire electromagnetic spectrum, okay? You'll notice words here that you recognize. So like radio waves and microwaves and infrared. Here's the colors that we can see. Here's UV, ultraviolet light. Here's X-rays. Yes, quite literally, the X-ray machine that takes pictures of your bones, that uses X-rays. And then we also have gamma rays. I know that's a funny sign. It's like an 8 without the top. Okay. So this is the entire spectrum at a glance. Okay. What I've done is I've put this in a table for you. Like I said earlier, don't try and memorize it all in one go, okay? First, memorize the order. Radio waves, microwaves, infrared, visible light, UV, X-rays, and gamma rays, okay? First, try and organize those. Sure, guys, we're getting to examples, I promise. I promise, I promise, I promise. Okay, and then the visible spectrum here, the colors that we can see. Okay, so here's the table. Okay, I want you to take a screenshot of it. Okay, like I said, first start by memorizing the order and do what it does. So link up the type in order with its characteristics and its users. Okay? Then memorize either the frequencies or the wavelengths, because all of these have a speed of 3,0 times 10 to the power 8 meters per second. So you can use the speed of light and the frequencies to calculate the wavelength. Or if you can memorize the wavelength, you can use the wavelength and the speed of light to calculate the frequency. Okay, this is a lot, I'm aware, okay? I'm so aware that this is a huge table and that there's so many numbers to remember, okay? That's why I say start with type in order and what it does, and then add one of the other two columns in, okay? These values are not blocked, okay? These are ranges. It's not a precise value, it's a range. Radio waves have a frequency of between 1 million and 1 billion hertz, okay? And they correlate with a wavelength of between 10 meters and 0.1 meters, okay? So radio waves is literally radio waves, okay? That's what we use when we talk on our phone, when we watch TV, all of those are radio waves. Must we memorize the whole table? Yes, eventually. E2, the table is in the drive, which I will give you guys a link to again at the end. Okay. Yes, you need to memorize the type, what it does, and either the frequency or the wavelength. Okay. But if you have a teacher that asks it like this, they're very mean. Okay. I normally ask, what are radio waves used for? Give a range of their frequency or something like that. Okay. All right. Now, the visible spectrum. The colors we can see: red, orange, yellow, green, blue, indigo, and violet. Also have wavelengths, but these are in nanometers and they have frequencies in terahertz. Okay. Now with these, whoa, you do not need to know the wavelengths and the frequencies. Okay. You just need to know that red light has small frequencies and violet has large frequencies. Okay. That's what you need to know from this table. I don't know how, I don't like asking this. Okay, I give you a table with all the ranges. Okay, but it is in the curriculum. Okay, guys, so you don't need to know these. I gave them to you for interest's sake. All right, but you just need to know red has got short frequencies and violet has got long frequencies. I know, sweetheart, I know all of this is quite a lot. I get it, okay? That is why on Friday we're going to look at a couple of wave questions, okay? So you guys have a better idea of how it can be asked in a paper, okay? Now, you remember that formula there? Remember the formula for wave speed, okay? We've said that EM waves has got a speed of 3,0 times 10 to the power 8. Okay? Fact, all EM waves. So if you, instead of using wave speed here, use speed of light, okay? Then you can calculate wavelength if you have frequency, or you can calculate frequency if you have wavelength. This is what we're going to use tomorrow to calculate how much energy a wave has because of its frequency. Okay, so that's why today's section almost has no maths in it, okay? No examples that I can show you, because tomorrow we're going to take this, okay, this into energy. Miss P, a lot of electromagnetic stuff is going to come back in tomorrow, okay? And on Friday, when I do the past paper with you guys, okay, I'll show you the type of questions that normally gets asked for waves in grade 10. Okay, right. Now this means that if I know the frequency, I can calculate the wavelength. If I have the wavelength, I can calculate the frequency, because I always have a speed of 3,0 times 10 to the power 8. Okay, like I say, guys, the maths for this come in with the energy. Okay, but to give you energy today as well, we're going to pop your brains. Okay, so the maths for EM waves come in tomorrow's section. Okay, guys. Now, this is a bit of an introduction to tomorrow. The higher the frequency of a wave, the stronger it is, the more it penetrates, the further it travels, the more energy it has. Okay? And all around us, we actually have electromagnetic waves. Electromagnetic waves come from the sun, okay? And from different vibrations and things. All right. So the problem is that we as humans are constantly bombarded with radiation. Okay, not radioactive stuff, okay, just with radiation. Okay, and some people work in environments where they are more affected by radiation than others. Okay, so we need to know what amount of energy do waves have, so that we can protect ourselves from it. Okay. So waves transfer energy, and we have to protect ourselves because energy could damage our cells. Okay. One example of this, when you go out and you go have a tan, okay, the UV light, the UV rays that hit your skin causes your skin, the pigment in your skin, to become overactive. Okay, it's called melatonin. Okay, and so that is what gives you a tan, right? But when these cells become active, there is the possibility that the UV light that causes the tan can also damage your cells, okay? And that's when you burn, and that is when you get skin cancer, okay? So that is why it is important to know that certain frequencies do more damage than others, okay? So UV light can damage our eyes, and it also depends on your eye and your genetics. Some of you will be less prone to getting UV light damage. Some of you will be more prone. Okay, it's all how we are put together. Okay, I know this is going to be difficult to remember, Ollie. Okay, now question I get asked a lot: radio waves are used in cell phones. Okay, but radio waves have low frequencies. Okay, so they have low penetrating power. Now, that's not to say that they don't cause damage. Okay, radio waves can cause damage. Any wave can cause damage. Like if you work if you are an X-ray technician, you have to protect yourself against the X-rays, okay? Because those X-rays have energy, okay? But it's got low frequencies. So the energy it carries is less, so the chances of it doing serious damage is also less. Okay. Right, guys, before we finish off, please have a look at the Q&A where you are now. Oh, and of course, I sent you the link to today's thing, hey? Oh, man. Ooh, Let me just undo that action. There we go. Guys, please, please, please don't use the link I sent you, the first one. I somehow sent you today's link. My brain's not working. Okay, so I've sent you the drive. Itu, you asked for the notes and stuff. If you click on this drive, Itu, it will take you to a drive. If you click on this link, it will take you to a drive in which you can find all the resources. Okay, guys, the link I posted earlier, I'm pretty sure it was today's link. Here at the bottom is tomorrow's link. Please, please, please use this one here at the bottom. Don't use the one at the top. Okay, right. We've got roughly 5 minutes left, and I got lots of, ma'am, can we look at that again? Okay, so let me go back to what is important. Okay, and I know this might not be what confuses you, but let me go back to what is important. Whoops, that was a door. Okay. This part here is important. How they propagate. Okay, how they propagate and the energy they carry. Itu, the first one that I posted is the link to the drive where all the resources are in for you. The second link is the link to tomorrow's lesson. Okay, so guys, this is what is important, how these waves generate. Okay, and again, it's really hard for you guys to understand because you haven't done anything on motors. I get that. Okay, I get it. Have you ever heard when you drive underneath electrical cables, they make this buzzy sound? Okay, they're major buzz sound. They do that because the electricity running in the cables actually causes a magnetic field around them. And that magnetic field that it causes around them makes the air static. Okay, it's not the electricity in the cable that makes the air static. The electricity cable causes a magnetic field around it, and that magnetic field causes an electric field exactly next to it. But our electricity, oh, I forgot about the homework, my bad. Okay, tomorrow, I'm making a note, okay? I'm assuming I'm gonna add it in the beginning of tomorrow's slide now, okay? Ionization is the bad stuff. Sure, guys, all of it's very, like, still under-researched and all of that, okay? I don't want you to panic too much about it. Our bodies are like amazing. Our bodies adapt to flipping everything. Okay. Right, has anyone got more questions? It's gonna take me like 90 seconds to see it. Okay, no one else got questions, guys? Okay. All right, guys. Oh, wait. Itu, the homework is going to be tomorrow. Okay. The homework is going to be tomorrow. So I will tomorrow morning start by marking yesterday's homework. Then I'm going to go through energy of EM waves, and you're going to see that EM waves are not quite that bad, okay? Then I will give you homework, lots of wave questions, and we're going to work and struggle through those wave questions on Friday, okay? Then you guys still need to remember, next week we have Tuesday, Wednesday, Thursday, okay? That is what we have next week. Monday's a public holiday, Friday's a public holiday, okay? Tomorrow, you need to tell me, are we going to do magnetics and electrostatics, or would you rather I do electrical circuits? We don't have enough time next week to do all three, okay? If we had a 5-day week, we could have done it, but we only have a 3-day week. So I can either do magnetism and electrostatics, or I can do electrical circuits. Okay, so tomorrow morning, tomorrow when I see you, I'm going to ask you that first, okay? And we're going to have a majority vote on it. Okay, so if you have a strong feeling of what you want to do, tell me. All right, guys, thank you for joining. You know I love you. Have a fantastic day, and I will see you again tomorrow, same time, same place. Bye.